Okay, so what I want to do today is I want to take a look at a slightly different type of problem. We looked at problems like this, where when we extended this out, that this slope piece came in and was tangent to the circle. This time it's not going to be tangent to the circle. I will tell you that the distance across here is 40 millimeters. This height is 20 millimeters. Those two numbers are very significant. What does that 40 millimeters and 20 millimeters tell us about what is going on with this circular portion here?
Diameter, radius of the circle?
There you go. It tells us that is actually an exact half circle because the distance across is exactly double the height. So that, yes, that is a diameter and a radius. At some point, if we get ambitious, we might do an example where this height is not half of that distance across, so that it would not be half a circle. That becomes a much more complex problem. This time, rather than just having you find this distance, we had you find that distance x before. This time I am going to tell you that this is 12 millimeters. And this here is 8 millimeters. And this is a 1:4 slope. Aspect ratio. We're going to ask you to simply find the area of this piece. Now before, because this was tangent at that point before, we were able to cut it with a radius back to the center of the circle, and that was a right angle. But this is not tangent anymore, so that is not a right angle. In fact, we know that that has to be an obtuse angle. How do we know it's obtuse? Well, if it was tangent, it would have to be a right angle. It can't be acute because that would mean it would have to be sloped down into the circle. So it has to be out here further. It has to be obtuse. An acute angle would not have hit the circle correctly. When we were looking for this dimension, we had to do vertical and horizontal triangles. We broke it up something like this. Well, now since we have that dimension, we don't have to go through that trouble. There's a little bit easier way to approach it. We can just cut it right across here like this, using that right angle. The reason that works is that triangle there, that I'll redraw in green here, we have both legs. Of course, this leg here is the 8 millimeters. What's this leg down here going to be?
32.
Perfect. Yes. Half of the 40 makes it 20 here, plus the 12 is 32. Good. That's 32 millimeters. Now we can actually find the third side rather quickly. If we have a right angle and we know two sides, we can find the third one using a squared plus b squared equals c squared. 32 squared plus 8 squared, square root. We get 32.98 millimeters. So barely bigger than the 32 base. Next, we can find our angles. Really doesn't matter which one we find. Let's find this one down here just because that's what we're more used to looking at. How am I going to find that angle?
Tangent.
Give me a tangent. You got it. Tangent of an angle equals opposite over adjacent. What's the opposite side there?
8.
8 and the adjacent?
32.
32. So now how do I solve that for the missing angle?
Verse 10.
You got it. Inverse tangent of 8 over 32. I believe that is, let me check my modes quick. I believe that's like 14.04 degrees. It is 14.04 degrees. That makes this angle here 75.96 degrees. So we know everything we could ever possibly want to know about that triangle. We know all three sides and all three angles. While we're at it, let's find the area. The area is just going to be the 8 times the 32 divided by 2, or 128 square millimeters. Next, let's move on to this purple triangle up here. We know two pieces of that triangle. This was a radius of the circle, so that's 20 millimeters. And this piece over here we found to be 32.98. So we need at least one more piece. We either need an angle or we need the third side. Well, it looks like we can't find any of those pieces here, but let's explore this corner right here a little more closely. That corner can actually be broken down into two separate pieces. If I cut it like this angle here is a right angle because the vertical and the horizontal components coming together. This angle right here comes from our 1:4 aspect ratio. Think of it as being a triangle like this with a vertical aspect of 1 and a horizontal aspect of 4, or dimension of 4. So how do I find that angle? Inverse tangent of 1/4. Yep, I heard you start it there. Which comes out to be 14.04 again. So what that tells us then is that this complete angle from here all the way to here has to be how big? This one right here. What'd you get?
104.
104, good. 90 plus the 14.04, yes, 104.04 degrees. So that means this whole angle is 104.04, which means we can now find this angle here. Because we take our 104.04 and subtract how much?
Yep.
75.96, good. So we subtract there, we're going to get what's that, 28.08 degrees. This angle is 28.08. In your notes, I want you to take a couple minutes and see if you can remember how to find that angle right there in red. We'll go over it in about a minute. In this case, we have three pieces of this triangle. We have two sides. Oops, that's not what I want to do. We have two of the sides and one of the angles. Anytime that we have three pieces of a triangle, we can find the other three. Remember, there's 6 total pieces, 3 sides, 3 angles. We just have to decide what process we're going to use. The first question is there a right angle? Because if there's a right angle, we just use regular trig. Sine, cosine, tangent. There is no right angle here. The second option is, do we have a side and its opposite angle? Because if we have that, what process do we use? We have one side and its opposite angle plus a third piece. We can always use the law of, not cosines, just sines, right? The third option is if we have two sides and the angle in between them, we call that the included angle. Then we would have to do law of cosines. So in this example here, we have one angle, the 28.08. The big question is do we have the opposite side? And we do, the 20 millimeters. So we can use our law of sines. It'll be the 20 millimeters over the sine of 28.08 degrees equals, well, our only other piece of information is the 32.98. Is that going to go on top or bottom?
This.
We can go on top, yes. 32.98 millimeters. Did you ever figure it out, Wayne?
Yes.
Thank you, sir.
Yeah.
So I'm going to label this angle up here. I'm going to call it angle B. So that's going to be over the sine of angle B. So here for this proportion, we're going to cross, multiply, and divide. Now, this is what we're looking for, is the sine of b. So we cross multiply this way and divide by 20. So it is the sine, come on, 28.08 was my parentheses, times 32.98 divided by 20, giving me 0.7762. What do I have to do with that? Well, first I'm going to do an inverse sine. Second sine, second answer. Gives me 50.91. But notice I did not put B equals there because that is not angle B. How do I find angle B here? Because it's an obtuse angle, we have to find the supplement. It's 180 minus the 50.91. That's 129.09 degrees. While we're at it, we just as well find our third angle down here by subtracting. It's 17.93 degrees, I believe. Nine three or is it 8.3? Must be 8.3. It is, should be 8.3. Subtracted way wrong there. Let me try that again. It's not 17.83. It is going to be 22.83. There, that looks better. Now, there is a reason for finding area of that piece. There's a reason we wanted to have this angle. Because what we have right now, we have an angle and we have the two sides next to it. In other words, we have two sides in the included angle, which if I were solving a triangle would be a law of cosine situation. But I've already found the other angles for this triangle, so I'm not worried about the law of cosines. I want to find its area. And I showed you guys a shortcut formula yesterday for finding area. If I have sides A and B and angle C, the area of a triangle is A times B times the sine of angle C over 2. So that'll allow us to find the area of this triangle without having to find the third side and use Hero's formula. That would be a little clumsy here. So we have 20 millimeters times 32.98 millimeters times the sine 22.83 degrees over 2. Here's 127.96 millimeters squared. That's going to go with our 128 here. It's kind of amazing that those two triangles came out to be so close in area, within 0.04 of a square millimeter. The last piece we need to find is our sector of a circle. To find the sector of a circle, we know we have a 20 millimeter radius. We need to know this angle. Well, to find that angle, we're going to use this angle, that's this here, 14.04. And this angle here, which is the 22.83. And subtract them from 180 because this is a straight line here. So those 3 have to add up to 180. So what is that? 36, 143.13 degrees. So now we can find the area of that last piece, that sector of the circle. It's pi, 3.14, times the radius of 20 squared, times 143.13 over 360. It was 499.36 millimeters squared. So to that we have to add the 127.96 millimeters squared and the 128 millimeters squared. Okay, 755.32 millimeters squared is that area. So we've done a lot of problems with this half circle or segment of a circle. We've done some problems like this where that wasn't a full half circle. This might be 60 millimeters, and this might be 18 millimeters here. But this did not have, when we did it this way, we didn't have that extra little piece on the end. If we had this extra little piece on the end, this was always a full half circle in here. The reason for that is it's absolutely impossible to find the area if you have that extra little piece out there, unless this is a full half circle. Now, that doesn't mean we can't find the area of it. It means we can't find the area of it the way it's drawn. We would have to change it into a problem that we know how to find the area of. So let's look at a drawing like that here. I'm going to call this 60 millimeters here. And this is going to be, do I want 18? Yeah, 18 will work. 18 millimeters there. And then I'm going to come out here 10 millimeters, 6 millimeters, and we're going to do a 1:3 aspect ratio there. If I want to find the area of this, it gets to be a really ugly problem. So let's do it. Why not? What we actually need to do is we need to turn this, as I said, into a problem we know how to do. Well, if we expand this down to make that a full half circle, that's the problem we just did. We just need to know how far, what this distance is, how far we have to drop that down to make that full half circle. So now remember, we're going to look at this as a sector of a circle. In fact, what we're going to do, we're actually going to do this from the center up. That's 18. That cuts the 60 in half to be 30 and 30. What we're actually going to be finding at first here is the full circle, this distance all the way to the other side of the full circle. If I call that x, do you recall how do we find x? We've got 30 times 30 equals 18 times x. So to solve that, it's 30 times 30 divided by 18. Gives us 50 equals x. So 50 equals x. What's the diameter of our circle? 68. Good. So our radius is 34. You got it. So what that means is coming back up here, to make this a full half circle, this piece has to be 16 millimeters long. So that makes this whole thing 18 plus 16, or 34 millimeters. So this is 16 millimeters that was added down here. Now we can go ahead and find the area. I know that looks a little curved, but I'm being very careful not to draw it through that point, because it does not go through that point. The height of this triangle now from here to here is 6 plus 16, or 22 millimeters. The distance from here out is the same as what it was up here. It's just half of my 60, which is 30, plus 10 makes 40 millimeters. So we would have 40 millimeters by, what was that, 22? Millimeters, and we go from there. So I can find the length of this side here. It's the square root of 40 squared plus 22 squared. $45.65. You can find this angle down here. It's going to be the inverse tangent, 22 over 40. Here's 28.81 degrees, which makes this angle up here 61.19 degrees. Now I can find the area of that triangle. It's simply 1/2 of 22 times 40, right? Or 40 times 22 divided by 2. It was 440 millimeters squared for area. Next, I would move on to this triangle right here. Come on. I know that this is the 45.65 millimeters. And I know this is our radius of 34 millimeters. Once again, I can find this angle up here. I'm looking at this angle here, which I'm going to split into two pieces. I have the right angle for the vertical and horizontal components coming together. This angle here is the inverse tangent of my aspect ratio, 1 to 3. I believe that's 18.43 degrees. It is 18.43. That makes the entire angle 108.43. Subtracting the 61.19 gives us 47.24 degrees here for this angle. Now we could go through the process of finding this angle here. It's an obtuse angle, so we're going to have to remember to do the supplement, subtracting from 180. And then finding this angle here by subtracting these two from 180 and finding the area of that sector. Now the thing we have to remember, I'm not going to finish that process because we're running a little low on time. The area we find is going to be the area of this whole thing. But remember, we started out, all we really want is the area of that piece. So we have to subtract out all of this. So how do we subtract that out? Well, there's three pieces we have to subtract back out. The first one is very simple. It's this rectangle over here. That rectangle is 16 millimeters high, 40 millimeters long. Which is 640 millimeters squared that'll be subtracted out. The next pieces are a little bit more complicated. We have this triangle here, this right triangle. That's going to be 16 by 30. That one's not so bad. 16 millimeters by 30 millimeters divided by 2 because it's a triangle. That's 240 millimeters squared. But then finally we have this sector of a circle here. That sector of a circle actually has pieces here. This is 34. This is 34. We need to know this angle here. That angle there is going to be the same as the angle up here. So this angle would be the inverse tangent of opposite, which is 16, over adjacent, which is the 30. .07 degrees. So the area of that sector that has to be subtracted out is pi 3.14 times the 34 radius squared times our 28.07 over 360. Giving us 283.03. So if we add those up, we get 1,163.03 millimeters squared. That's the area of this bottom piece down here that has to be subtracted out. So you can see it almost doubles the work for us because we have to find that radius, we have to add on the radius down here, find the area of the whole thing, and then subtract back out the area that we added. But that is the absolute only way to solve this without using not even basic calculus, but some rather advanced calculus techniques. Now the good news is, I don't hate you guys that much. This one will not pop up on a quiz, at least not on an individual quiz. It might be one where I put the problem up there and say, okay, somebody go up to the whiteboard and work as a group and solve it, but I would never put it on an individual quiz and say, go to it, you got an hour, give me an answer. Even I have to be able to walk out in the parking lot at night without having to stop to listen for revving engines. Okay, so there is a worksheet attached in Blackboard. Problems are not quite as nasty as this last one we did. They're very similar concepts, finding the segment of the circle, and stuff like that, things that we've worked on. I will warn you, there is a quiz coming up this Thursday. In fact, this Thursday, I'm dedicating the entire class to working on a quiz. So what I'll do, those of you that are usually in class, remind me tomorrow. I will give you a hard copy of the quiz so you don't have to print it off. And then Thursday, I'll give you a couple of hints and reminders so that you can remember some of the things that need to be done for the quiz. And then we're moving on. Next week, we'll move on to compound angles. So that's it for today. We'll shut off the recording here. If you would like to get started on